Okay, so one of the few things we talked about in class was graphing and using our calculator to help us with exponentials. So if you go ahead and find page 66 in your workbook, we'll go over a little bit of calculator with exponentials. So not every question do you need your calculator for. A lot of the tools that we've been using in class, we can still use. And then the things that we don't have tools for by hand, we can then rely on our calculator. So looking at number 1, yes, we're given this function. It says, so we want to enter this equation in our graphing calculator. So if we go ahead to our y equals, and then we're going to type in 3 times 2, and then we'll use this caret. Let me move it so you can see. We'll use this caret symbol to do our exponent. So to the, and then up there we'll type x plus 2. And then we're going to have to arrow over so that we get out of the exponent and then type minus 1. So we have it typed into our calculator. If we hit graph, we'll see if it shows up how we would like it to show up. Pretty good. We might need to change our window a little bit to see that y-intercept, but we'll check that in a little bit. So as we keep moving, so the first one is, what is the equation of the horizontal asymptote? We don't really need our graphing calculator for that. We know that our horizontal asymptote is at y equals 0 unless our graph is being moved up or down. So this minus 1 meant our graph moved down 1. So that would mean that our horizontal asymptote also moved down 1, so we're at y equals -1. Again, we don't need our graphing calculator. Looking at our picture, we can tell that it went underneath 0, but then is not really traveling any farther down, so that kind of matches our idea at being at -1. So then if I want to find the x-intercept, we found x-intercepts before. Remember that second, calc, and then 0. So from here, we'll hit the second button, calc, and then go to 0, and then we have to figure it out. So we have to find our little toggle, and we have to be to the left of the x-intercept, then to the right of the x-intercept, and then we'll guess by getting as close to that x-intercept as possible. So I found that that x-intercept, or that 0, is at -3.585, 0. Okay, so then if we want to go ahead and find the y-intercept, again, these are the same functions we've done on our calculator before. So the y-intercept, we do second calc, and then we go to value and make x equal 0. So when we do that, we get 0, 11 as our y-intercept. And then the next one, we want to know when y is 4. So this is a little different. We have done this before, but remember we have to make another y value and then find where the two graphs intersect. So we would go to y is 4 graph, and now we know where the y value 4 is, and we want to know where our graph intersects that, and that'll tell us what the x value is when y is 4. So we'll hit second calc, go to intersect. Then the first curve means is your toggle somewhere on the blue line, the first graph that you drew. It doesn't matter where, as long as it's on the blue. Then it needs to be on the second curve, which is the red one, and then we guess by getting as close to where those two meet as possible. So when y is 4, x was -1.263. And then we really don't need our calculator. We can look at the picture to tell us the rest of this information. But we don't really need it because we've done this information before. So our domain, again, of our exponentials is always -infinity to infinity. Our range, remember that horizontal asymptote is now at -1, so we go from -1 to infinity. And then we know, because if we look at the picture, it's growing from left to right, or also by looking at the equation, it's a whole number to the x power, that this is exponential growth. So do one more together and then have you try one on your own. So if we look at number 2, again, the first thing we'll do is we'll type it into our calculator. So we'll go back to y equals, and now we're going to do 4 times, And then I would probably put the 2/3 in parentheses, 2 divided by 3 to the x power. So again, using that caret to the x power, and then plus 3. We have to make sure that we arrow out of the exponent to get that plus 3, not in our exponent. So then if I hit graph, there it is. All right, so now we're just gonna again go find all of these pieces. So if I wanna find my horizontal asymptote, remember we don't really need our calculator to do that. We know since our graph moved up 3, that our horizontal asymptote also moved up 3 to y equals 3. Then to find our x-intercept, that is when we do our second calc 0. So if I go to my calculator and I hit second calc and then go to 0, and then I'm looking for the x-intercept. As you can see, from what we see, it's really not crossing the x-intercept anywhere in our current window. So then you have to question, is it going to cross at all, or is it just not crossing in the window that we have set out right now? Some things to consider is, where is your horizontal asymptote? So considering your horizontal asymptote is at y equals positive 3, and an exponential never crosses the horizontal asymptote, that means that graph is never going to be lower than 3. So it's never going to get to an x value, or it's never going to cross this x-axis, right? Because it's stuck above 3. So there actually is no x-intercept here. So that doesn't mean that works for all of them. Sometimes it just might not be in the window that you have. But if your horizontal asymptote is bigger than 0, 0 or bigger, there is not going to be an x-intercept. So then if I want to find the y-intercept, again, I'm going to hit second calc. This time I'm going to do value. And when we do value, y-intercepts always come from x equaling 0. So I'll come second calc value. I make x equals 0, and it tells me when x is 0, y is 7. So my y-intercept is at 0, 7. So then to find when y is 4, remember that's when we graph y2 equals 4. So we go back to our y equals, we make y2 equal 4, and then we're going to find where the two graphs intersect. So then we're going to use that second calc intersection button. So second calc intersect, first curve, second curve, and then we're got to get as close to that intersection as possible. So when y was 4, x was 3.419. 3.419. Good, so then again, the rest of this, we can use the picture to help us, but we don't need the picture to help us. But it's always helpful if we look. Our domain is negative infinity to infinity as always. Our range, with our y-intercept moving up 3, our range moved up 3. And then with growth and decay, because your graph is going down, it's decay, or also what is being raised to your exponent is a fraction less than 1. So we should know that this is exponential decay. All right, go ahead and try number 3. I would pause the video, try to fill out as much of number 3 as you can, and then I'll post the answers. I'll show you the answers so that you can check them. Okay, so hopefully you tried number 3. Number 3 was unique because of this negative in the front. So when you graphed it, you did get a graph that was actually flipped upside down, so it looks something like this. It's still an exponential function, it's just that negative had flipped it over the horizontal asymptote. So a lot of the information was still the same, and how we found things was still the same. So our horizontal asymptote was still at y equals 4. It was just now above the graph, right? If we looked, we could have this dotted line up here, and now my graph was going this way. My x-intercept we still found by doing second calc and then 0. My y-intercept we still found second calc value, making x equals 0. So all of it was still the same, just looking at the picture. It just looked a little different than the examples above. Y equals -2. Again, we draw that line, y2 equals -2, and find that intersection. So second calc intersect. It does affect the domain and range. The domain, it does not. It's still -infinity to infinity. But now your range, instead of going to 4 to infinity, it's only using these negative values until it gets to +4. So -infinity to +4. And then though it is upside down, it is still considered exponential growth, because remember, you are still raising a whole number to the x power. So that is still considered exponential growth. So hopefully this was some good practice, a little reminder on how we can use our calculator as we move forward and start to look at these problems in context. We'll rely on our calculator a lot more as we're working with bigger numbers. So actually we're gonna go ahead and move forward to page 71. So if you'll go find page 71, we'll get started with those notes. So on page 71, the first thing we're going to talk about when we talk about exponents in context, or exponentials in context, is when something is a factor. So this is our normal formula, right? We've been working with this since we started graphing exponentials. But when we use it in context, these two values are important to us of what they mean. So the A value, that number in the front, is the initial amount, how much you're starting with at the beginning of time. Then B is now your factor. So things that indicate that you're working with a factor would be if something doubles or triples, or if something is cut in half. Cut in half, cut in a third, a fourth, right? Any fraction that they're listing, a fourth of something happening, things like that, all represent a factor. So double, you could even go quadruple. But all of these, right, these are like you're increasing, like by 2, by 3, by 4, and then this is cutting in half, so you're multiplying by a half, a third, a fourth. So all of these represent a factor, which would then, these would be what represents that B value. And then X usually represents time. In most cases, we're going to use that as the time, years, months, days, or whatever our context of our problem is. So again, A is our initial amount, starting amount. B is our factor, what is it increasing or decreasing by, and then X is that time. So if we look, I'll look at the first two examples and then have you try two on your own. So it says, bacteria can multiply at an alarming rate when each bacteria splits into 2 cells, thus doubling. So doubling is a good indicator that we're looking at a factor. If we start with only one bacteria, so one bacteria, and it doubles every hour, write an exponential function that models the growth of the bacteria. So we're starting with 1, so the value of A is 1, and then it doubles every hour. So then doubling represents that it would be times 2. So again, using this equation here, we would have y equals 1 times 2 to the x power. And X, remember, represents every hour. So then it wants to know how much is present after 24 hours. So when X is 24, so if we solve Y equals 1 times 2 to the 24th power, and again, with our context problems, we're going to use that calculator a lot since 2 to the 24th is a lot. So if I do 1 times 2 to the 24th power, I get a very large number. So I get 167777216. So 16 million bacteria. All right. So let's go ahead and look at another problem. So each year the local country club sponsors a tennis tournament. Play starts with 128 participants. So we're starting with 128, meaning that our starting value is 128. A is the starting amount. And then during each round, half of the players are eliminated. So half means that our factor, right, we're cutting it in half every time. and then it wants to know the exponential function per round. So in this case, x represents how many rounds there are. So I can write this as a, so 128 times 1/2 is our factor to the x power. And then if it wants to predict how many players will be in 5 rounds, we would make x equal 5. So 128 times 1/2 to the 5th power. Again, using our calculator, 128 times 1/2 to the 5th power says 4. So after 5 rounds, there are 4 players left. All right, so go ahead and pause the video and try these last 2, and then we'll go from there. All right, so hopefully you tried number 3 and 4. So 3 was starting with 120 milligrams of caffeine, and then it was 1/4. So our factor was 1/4, and then it wanted to find after 5 hours. So when I made x5, I got 0.117 milligrams of caffeine. And then number 4, we started with 5 pieces of clothing. It quadruples every day. So x represents the number of days. So then we had 5 times 4 to the x power. So then it asked at the end of the week. So there are 7 days in the week. So we wanted to know when x was 7. And I got 81,920 pieces of laundry. I hope you never get to have that much laundry at one time. That's a lot. Okay, so we're going to keep going with this. These word problems feel pretty easy, kind of pretty easy to set up. So let's go ahead and work on and find page 72 and go over those. Okay, so on the front, we talked about a factor, so like doubling, tripling, quadrupling, halving, a fourth, cutting it in a fourth, whatever the case may be. If they give us a percent, we have to do a little bit of work to find that factor or that b value. So what we're gonna end up doing is 1 plus or minus whatever percent that they give us. Now we have to be careful. We have to write the percent as a decimal. So we have to take the rate and write it as a decimal. And then plug it in here. So if it's growing, this is when we're talking about growth, this is when we would use 1 plus r. If it's decaying is when we would use 1 minus r. So you have to, in the context, know which of the 2 you're using, and then by finding that growth or decay, you'll be able to find your rate. So looking at these, just to find that factor, practice finding that factor with this new computation. So growth by 12%. So first we have to turn 12% into a decimal. If you remember about turning something into a decimal, you move it 2 places. From a percent to a decimal, you move the decimal 2 places to the left. So this would be 0.12. So then if we're talking about growth, we're going to do 1 plus 0.12, which would give us 1.12, right? So that b value would be 1.12 as our growth. So same thing here, looking at number 6, if I want a decay of 4%, first we need to turn 4% into a decimal. So again, taking this whole number, we'll move our decimal 2 places to the left. So this is 0.014. And then because we're doing decay, we're going to do 1 minus 0.014. So when I do 1 minus 0.014, I would get 0.96. And then one more, and I'll have you try some on your own. Again, we're going to turn our percent into a decimal first. So 28%, we'd move the decimal 2 places to 0.28. And then because we're looking at decay, we're going to do 1 minus 0.28. And 1 minus 0.28 would give us 0.72 as that factor, that b value. So it's a little different when we're working with our percents rather than when we were working with our doubling, tripling. So go ahead and try 8 through 10 and find those b values on your own, and then I'll go over them and have you check your answer. So hopefully these are the B values that you got. Something that you can always do to check yourself is if we're talking about growth, your number should always be greater than 1. If you're talking about decay, your number should always be less than 1. If it's not, that might mean that you used the wrong equation to make your factor, but you might want to go back and check that. So again, we're going to go back to how we can use this in our word problem, and really, there's not much difference in the setup. We're still using this y equals a times b to the x. A is still that initial value, right? A is still the initial value or the starting value. And then b now is still that factor. It just might take a little bit of work to figure out what that factor is. So again, I'll go over a couple with you and then we'll try some on our own. So the first year of a charity walk event had a attendance of 500 people. So the value, that starting amount was 500. And now the attendance increases at 5% per year. So as soon as you see a percent, you know that you're working with this rate instead of a factor. So we're going to turn that rate into a factor. So first, we need to turn 5% into a decimal. So again, 2 places to the left would make it 0.05. So then to turn that into a factor, we're going to do either 1 plus or 1 minus this R value that we just found. So since it increases, that means it's growth. So we're going to do 1 plus 0.05, which would give us 1.05. So now this is the factor. We turned our rate into a factor, and now we can write our exponential function. Y equals 500 times 1.05 to the x power. And then since x represents years in this case, it's increasing every year. It says predict how many people will attend 10 years, so when x equals 10. So if I take my equation y equals 500 times 1.05 to the 10 power, and we'll type that into our equation, 500 times 1.05 to, close my parentheses, to the 10th power. I get 814.447. Now remember, we're talking about attendance, how many people. So we're not going to keep that as a decimal. Yeah, you have to be cautious or conscientious about what you're talking about, what your units are. So I'm going to round this to the nearest whole number. So since that's 0.4, we wouldn't round up. So it's just going to be 814 people. Yeah, so you always want to be careful what units you're using to how you should be rounding. And if you're not sure, I'll tell you how many to round to. So for instance, if you're talking about something, you're like, I'm not sure if this could be a decimal or not, I would indicate how many decimals to round it to. All right, so let's look at number 12. So it says your starting salary in a new company is $34,000. So that would be your initial value, $34,000. And it increases by 3% per year. So again, that's going to be my rate. Since we're working on a percentage, we need to turn that into a factor. So we're going to make that a decimal first. So 3%. If we move the decimal 2 places, would be 0.03. So then if we want to make that a factor, first we have to figure out, are we going to do 1 plus or 1 minus? Since it increases, that's going to be 1 plus 0.03. Which gives me 1.03 as my factor. So now that I've turned my rate into a factor, I can write my equation y equals 34,000 times 1.03 to the x power. And then it wants to know after 20 years, so since x represented per year, we're going to make x equal 20. So 34,000 times 1.03 to the 20. 3 times 1.03 to the 20th power is going to be 61. And now again, you're talking about money, so you would be allowed to go 2 decimal places, 0.78. So this would be your salary after 20 years. Okay, so go ahead and pause the video and try these last 2. And then we will be done with our notes for today. All right, so looking at these 2, both of these we're talking about decreasing, so we should have been using our 1 minus here. So when I turned 15 to a percent, or to a decimal, I got 0.15. So 1 minus 0.15 would give me 0.85. So then I gave my exponential function as my initial value times this. And so then I wanted to know when x was 5, so I made x 5, and I got $18,857.48. And then for number 14, I started with $25,000. My rate was 6%, so 0.06. So 1 minus 0.06 would give me 0.94. So that made my exponential function. And then I wanted to know after 7 years, so when I plugged in 7, I got $16,211.94. So hopefully you feel pretty good about these examples. We'll go into more of this after we come back from spring break, but this is just a good introduction. And then we took the test in class, so if you need to make that up, make sure you reach out to your teacher to make that up.